please. This is going to take a while, so I would like to get started so we can have lunch eventually.
Dr. Combs is gone, Dr. Davis is gone, so now I can be real.
Okay. All right, my thesis topic was the derivation and comparison of deterministic and stochastic predator-prey models. Mathematicians and researchers are always looking for new and different ways to model real-life biological situations. Some of the most commonly modeled phenomena are predator-prey systems, competition between two species for some kind of a nutrient, and also the effects of disease on a species. The models that people have, or the studies people have done in the past typically fall into one of these four categories. They either primarily focus on a deterministic model, a stochastic model, a comparison between the two with some kind of preference for one or the other, or they believe that both are equally valid and useful. One thing that these models actually, or that these studies have actually had a shortcoming with in the past is that they really focus in a very narrow scope. So the results are only applicable to a certain number of studies outside of that particular one, outside of that particular situation. So we wanted something that was a little bit broader, that could be applied more uniformly for more types of situations and everything, because as anyone who is in mathematics knows, if you can get some kind of a generalization, it is extremely valuable. And also, it's very difficult to find any kind of derivation between one type of model and another, a very rigorous derivation, so that's what I was trying to do with these. First of all, I don't know how many of you know about deterministic and stochastic models, so we'll just sort of go through the definitions. Determinism is the belief that everything has a predestined end, which is governed by natural laws. That essentially describes a deterministic model. The deterministic model is one that if you give it a certain set of initial conditions, run it 1,000,000 times, you are going to get the same result every single time. There are two types of deterministic models. There's the discrete, which utilizes discrete time intervals. Something in, like say, the flowering process of, or the flowering cycle of a plant will, we can use a discrete model for that. And that is modeled using difference equations. The continuous form is continuous time. It describes continuous time. We use differential equations for those, and if you think about the dynamics of the human population, those can be very well modeled by the continuous model. Stochasticity is lack of predictability. It is essentially the opposite of the deterministic model, so I felt it was pretty good for comparison. It obeys the laws of probability. It's based on statistics. It includes a random factor, and also each sample path, because it has that random factor, each sample path is going to be a little bit different. Every time you run this model with one set of initial conditions, you're going to get a slightly different result. And a stochastic process is just a collection of random variables, x sub t of s, where t is an index set, like time, and s is the sample space of x. So you can think of that as population size. And you can see the shorthand notation down here. The first one we'll use in the discrete case, the second one we'll use in the continuous case. Okay, the discrete and continuous notation look very similar. You have a collection of random variables that represent the population of species X, and probability is defined pretty much the same way in the discrete case. You have the probability that at time t, this species X is going to be of size n. It's the exact same thing on both sides. It's pretty much said exactly the same way. The biggest difference between these two, again, is just the representation for the random variables, for the set of random variables, and what actually represents the state or the size. probabilities are just how they sound. The probability that there is a transition from one state to another by the random variable x of t. Mathematically, you can see the representation here. It is a probability that the species x of t goes from state I to j in this time interval here. And if you write that all out, it is just the probability that species x is going to be at state j by time t, given that we know it was at state I at time s. That's like saying if you have a kid that's 5 years old, you don't have to know they were 1, 2, 3, and 4 to know that they'll to get the probability that they're going to be 6. So keep that in mind whenever I discuss what the Markov property actually is. Also, given that these are probabilities, they have to obey these two basic rules. Any set of probabilities you look at are going to obey these. Add up all the probabilities, it's going to be 1. Any of the probabilities just by itself, it has to be greater than or equal to 0. We can't have a negative probability of something. Okay, now the Markov property. First of all, let's call delta t an arbitrarily small amount of time. We want to squeeze it down so much that we can have at most one event occur in that little amount of time. The Markov property actually characterizes any process whose state at time t plus delta t depends only on the state at time t. That's like what I was saying, the child who's 5, we can figure out the probability they're going to turn 6 without having to say, okay, we know they were 1, 2, 3, and 4. The Landau symbol is something we use to get better accuracy, but it's the primary motivation for that. We said that stochastic processes dealt with a random factor. This is the random factor. It is used to describe the probability of a rare or random occurrence. And just mathematically, you can see it as the probability, the transition probability, divided by the little amount of time as you take the limit. As the amount of time goes to 0, then the whole thing equals 0. So these transition probabilities are getting smaller faster than the time of the transition. Okay, the deterministic simple birth and death models. We'll start out just looking at the simple birth. We can make these 3 basic assumptions. There are no deaths, no interactions between individuals, and the birth rate is the same for all individuals. Let's just call the population at time t n of t. So logically, the population at time t plus delta t looks pretty much the same. So if we want to figure out, okay, well, what is this population after that little passage of time? Well, it is the size of the previous population plus this is the amount of births that occur during that little amount of time. Here's the birth rate, your initial population, little amount of time that passes. Add it all together, and you have what the population at that next time is going to be. Do a little bit of rearrangement, and we end up getting something very familiar looking, a differential equation. Okay, a step going from the single species birth to single species birth death model is actually very simple. First of all you have to do to make the transition from the birth model to the death model is substitute A for B, call it a death rate, and you've got it. So the same thing applies in this case. If you're going to do a birth and death model, you're just going to subtract the birth rate and the death rate, put it in where A was. You've got the birth and death model. The stochastic simple birth and death model, you have to derive it just a little bit differently, but generally the assumptions and things are the same. This is used if we want to find the overall probability of a particular outcome. In the discrete case, we'll do the discrete case first and then show how it sort of morphs into the continuous case so that we can use that later on. The assumptions for the discrete case are that the birth rate of all individuals is the same. Here we're going to call it the birth rate times delta t. The probability of more than one event occurring and time delta t is negligible. So we're just going to let the Landau symbol for now equal 0, just to keep it very simple. And also, this may seem sort of trivial, but it's still good to list it. If no time passes, the probability that the population equals the initial quantity is 1. So if no time passes, you have what you started with. Okay, well let's suppose that we want the probability of having a population size n. So we have to look at the separate cases for that. And let's suppose that we're only looking at the case where births are possible or no births. So case 1 is where there is a birth. So you start off with population size n minus 1, and you apply the birth rate, the time passed, and the probability of that particular case occurring. Case 2 is if there is not a birth. So that's just as if you had a birth with population size n, take the complement of that, that signifies no birth. Okay, combine the two, you can see here and here, and that gives you the total probability that at this next time step, we're going to have population size n. Figuring out the one for death rates is actually very similar. You got the probability that the population was n plus 1, and you had a death, times the probability that that case actually occurs. Same thing over here. This is the case where no death occurs. Combine the two for the overall probability of having population n, and here is this term, here is this term, and then this one is just these two combined. Okay, from cases 1 and 2, we're just going to use those as a guide to construct what the transition probability notation looks like. This is the probability that we have a transition from size or state n to k in this time interval equals the probability that it will reach state k at time t plus 1, given we know that at time t it was at state n. And you can sort of tell that this is exactly the same as what we were looking at. Here's as if there was birth, k equals n plus 1. Well, if k equals n plus 1, then that means there was a birth between the two. So there's your transition probability birth rate. If there is no change, then there's no birth. And then the last one, we assume that if any other thing were to occur, we call that probability 0. So this is any other case. For future slides, we need to know the notational difference. This just gives more mathematical practicality. This is the birth rate of sample size n, birth rate of sample size n. And same thing for the probability of no birth.